Unfortunately, it's, this movie I made, I don't know, 3-4 years ago. And at that time, I had a lot of time. So, I would show this movie and relax. But now, I don't have much time, but movie's still same. So it goes back and forth. I mean, that's simulation. This is real. It's not real-time simulation, but it's real simulations. And in MD, all atom MD, we cannot do it. We cannot, because we'll get nanoseconds. We will get picoseconds. We'll most likely get 1 or 2 nanoseconds. Whereas in here, we can go to half microsecond. So these methods allow us to look at longer timescales. And see, now it's unbound, and now it floats around, goes away. Okay. So I'm going to skip this, and I'm going to explain this to you, and then I'll conclude. So now we did this many, many times, 1,000 trajectories here. And what you see is that you have 2 peaks here. One peak, it's better to look at this one. You have 1 peak and second peak. So basically, you have 2 most probable lifetimes, okay? 1 and the second lifetime. So you have it's bimodal distribution. So you have bimodal distribution, okay? And so recently, in 2004, after we have done this, but this has never been published, these guys made an experiment, and instead of applying constant force, they applied time-dependent force, just like us in the simulations. And what they have observed, they also observed bimodal distribution of the rupture forces, okay? They also observed bimodal distribution of rupture forces, and we observed bimodal distribution of times. I mean, this is forces. I can translate it to forces. So basically, they have bimodal distribution, we have bimodal distribution. Of course, they don't look alike because there's a lot of modeling involved, and it's not going to look precisely what they obtain because, first of all, they have completely different loading rates. They have piconewtons per second. We have newtons per second. So we will never be able to obtain something like this. But qualitatively, our results of our modeling agrees with what they find. And it seems to us that there's this huge conformational transition that occurs between LR1 and LR2 state that describes this catch-sleep transition, okay? And right, so let me summarize with the main results. So we proposed the 2-state kinetic model, and we think that this model captures the main features of the catch transition from catch bones to sleep bones, which is in turn determining the shear threshold effect in living cells, okay? And then we also were able to estimate the energy landscape parameters for p-selects and bones with PSGL1, with G1, and we can also do it, with for other pairs if we have data. And this is microscopic information, by the way, that experimentalists cannot obtain. So this information can only come through modeling, theoretical modeling of experimental data. So we were able to do it. So we have very important information. We have resolved very important information. And we also developed a methodology for coarse-grained models for simulation of protein-protein interactions. Typically, coarse-grained models are used for proteins, and now we have used this for protein-protein complexes. It's something new that hasn't been done before, and we have applied it to this particular pair. And we believe that we do see the evidence for catch-sleep transition from our Langevin simulations. And I thank you very much for your attention.
Thank you.